Hello and welcome to this lecture. So this lecture is going to be different from many of the other things we've been seeing. So far we've been looking at how to do linear algebra, how to understand the concepts of it, and all the exercises and examples we've been doing by hand. Okay, that's okay. It's good to get good practice. But today, most often, most commonly, all linear algebra is done on a computer. Any calculation you want to do with vectors and matrices, eigenvectors, Gram-Schmidt, whatever you want to do, you do it on a computer these days. And so it's important to know how to do that. Okay, so I'm going to give you a brief exposure to how to do it. But like all things on a computer, you will really learn it only when you do it. I can show you how some basic things are done, but you have to pick up the skill to go to that software, read its help files, look at the description of what the commands are, look at how to use that software the best you can. Okay, so that will be on you. So this is not included in the syllabus for questions or anything, so you can just enjoy and learn about how these things are done. Okay, so there are many popular platforms for scientific and algebraic computing. So the one that's most interesting from an engineering point of view, there are two types of things. I've sort of split it into two parts. One is what's called MATLAB. MATLAB is very popular in industry and in academia. It's very easy to use, particularly for signal processing. It started off with a signal processing focus, so it has so much in signal processing, communications, and all these things, and many other areas also today. Anything you name, MATLAB is there. It's a big company. It's a paid product. It's very expensive to have licenses, etc. So all of those are a bit of a drawback, but other than that, MATLAB is very powerful. Now, if you want to look at open source, alternative, free versions of sort of MATLAB like software, but free versions. Then you have Scilab. Scilab is an open source version, and then GNU Octave, which more or less is a MATLAB clone. So any command you have in MATLAB, you will also have in GNU Octave. So these are three things that I want to talk about. If you have the money, you can afford the licenses, and you can use MATLAB. Otherwise, you can use GNU Octave or Scilab. So these software are much more powerful than just linear algebra. But linear algebra is also in them, so I'll show you how to do that. Okay, maybe not too much. I'm not going to show MATLAB that much. I'll show only very little because MATLAB has extensive help. There's lots of courses. It's easy to learn, etc. So I'll just point you to that. Okay. Now there's also another type of computing platforms and software which is more closer to programming and those kind of things, and that is the Python notebook based thing. So a lot of people use Jupyter notebooks and code up a lot of things. And if you want to do that and you want to use linear algebra, the two main things that you will be using are NumPy and SciPy. So this is all Python based. Jupyter, NumPy, SciPy, as you can see, they're all Python based. MATLAB, Scilab, Octave are its own language. It's a different type of programming application. This is Python based. So if you have a Python background, you will find that Jupyter, NumPy, SciPy are easy to use. You can bring in the power of Python, do a lot of other things with Python like you can, and it's very useful. Okay, so these are the two types of things. So what I'm going to show you, instead of just talking about what these things can do, I'm going to show you a demonstration. I'll open up Jupyter notebook and then show you how to call on NumPy and SciPy, and then execute a few commands for you, just basic commands, and also show you how to get help. So most of these programs today, you search online, you get help, understand what a command is. There are multiple places to do that, and then try and implement it. So that's what I'm going to show you, and so let's do that real quick in this morning. Okay. So first is this Jupyter notebook. So for Jupyter notebook, you need to have somebody who's running a Jupyter notebook for you. You can run a Jupyter server on your own. You can download and run it on your desktop. It's very easy to do that as well. There are many applications available for it. But what I'm going to do is I'm going to use Colab, which is Google's Jupyter notebook, Python notebook type application. So because it's already there, I'm going to use it. So let me go to Colab. Colab looks sort of like this. So how do you invoke Colab? So when you want to invoke Colab, you're going to go to the URL and you're going to type in colab.research.google.com. So you can see it's been used quite a bit. So if you go click on colab.research.google.com and press enter, it will ask you for a login, and once you log in with your study email ID, for instance, you log in and then you get access to this kind of an environment. Okay, so I've blown up the the zoom here to make sure that you can see the text and all that. Of course, you will have much smaller text. The first thing you want to do is maybe connect. Okay, so when you click connect, it will connect to a processor on the back end so that you can actually run something. So you may want to wait. So you can see it's connecting to a compute engine backend and it's initializing it. And once it does that, it's connected. So now when it's connected, you can start using it. So the first thing you want to do in a Python notebook is to import some modules. Okay, so there are 2 modules we're going to import, or one is good enough. But anyway, I'll show you. I'll show you how to import. So import numpy as np and import scipy as sp. So if you're familiar with Python, you'll understand these commands really well. But even if you're not, so just imagine that these 2 that are commands that you have to type in to get any linear algebra going. Okay, so then Python notebooks work in a very simple way. So you can keep getting these blocks of text and code. You can keep changing it. So let me just do the text above it. So how do you go to this website? Is collab.research.google.com. Okay, so this is my thing. So collab.research.google.com is the URL. You have to do that, and then you import these modules. So once you import these modules, you can start doing linear algebra with it. So right, so if you want to get started, if you're a little confused, you can also do Google search, like for instance linear algebra using numpy. So let's say for instance you do that, right, linear algebra using numpy. So you'll get a lot of hits, and there'll be a lot of websites which tell you how linear algebra can be done on numpy. So I'm going to just invoke the basic help of numpy itself without going into any other details. So you can see here it has extensive help for linear algebra. There'll be a lot of text that maybe it's difficult for you to understand, but the first thing to understand is how to declare matrices and vectors. So let me just start with that. It's not fully given here, so let me just describe how these things are done. The first thing is to declare vectors, right? So how do you initialize a vector? Computer programs work with variables, right? So there should be a variable which should hold a vector for you. That's very easy to do. You can simply do like this, right? So you can say x equals, here is the command. You may want to keep this in mind. You have to say np.array. Okay, so this array is what numpy uses for storing vectors and matrices. Okay, so you can see, I mean, Colab is very nice. It will keep giving you help like this. You can see it's a little bit complicated if you're not used to programming a lot, and Python has a lot of technical text going on. So array is a very powerful object. It's like a specialization on the Python list. So you can do a lot of funky things with it. But for our purposes, we're going to use it pretty much like a vector, right? So what I will suggest is the following. So you have to do put a list here which will make it a vector, right? So for some reason it wants to keep giving me help. How do I get it? Okay, so there you go. So np array, this open brackets, close brackets, regular brackets, and then you have to put a square bracket, and then you can start inputting your vector. Okay, when you start inputting your vector, maybe you want to do 1, 2, 3. Okay, so you can do that. But what I'll suggest is you put one more square bracket here and make it into like a 2-dimensional vector. Okay, so this is just good practice when you're dealing with vectors and arrays, particularly for linear algebra, because when you have a 1-dimensional array, NumPy treats it differently. You know, for instance, if you want to do a transpose, you can't do a transpose on a 1-dimensional array. It will give you the same thing over and over again. Okay, so just to keep it consistent, I like to, when I'm doing purely linear algebra work, if you're doing other work, you can do 1-dimensional arrays. But if you're doing purely linear algebra work, I like to keep it as 2 dimensions, so that it's easy for me to do. Okay, so this is I can think of it as a row vector. Okay, so this is a row vector, and if you want to see it, you may want to print it. So what's happening here is I'm assigning this variable x to this np array, which is row vector, 1 row, just 1, 2, 3, and I'm printing it. So when you want to execute it, you can either click on this thing here, or you can press shift enter. Okay, so I'm going to press shift enter. So it's executing and it gives you the output. So it says, you know, think of this as the 2 brackets as, you know, the outer bracket says that it is a 2-dimensional array, the inner bracket says it's the first row. Okay, supposing I want to do transpose, right? So transpose, there is a very nice thing for NP array. So capital T is just transpose. So if you do that, you will see it gives you a column vector. So you notice the difference between when I printed x and versus print. So maybe I'll print instead of just putting it out, it says array and all that, it's a bit distracting. So maybe we can say print x dot t and then see what comes out. You'll see it. So you see this is a column vector, right? So notice the difference between the row vector and the column vector. There is an overall outer square bracket to indicate that it's a two-dimensional array, and the first row contains just 1. The second row, notice the second row comes below that, contains just 2. The third row contains just 3. Okay, so this is all format. So all computer programs will have such formats. They'll have some established formats for what they think of as a column vector, row vector, how they print it out, etc. So hopefully you see that this is working out very, very nicely. Okay, so you can also define matrices. So let's say I want to define a matrix. I can again do np.array, and you can now imagine how a matrix is defined. So you have to first put outer square brackets to indicate it's a matrix, and then you can define your first row. So maybe my first row is 1 0 1. Maybe and then you have to do the second row, right? So for that you just put a comma and then do this again. So 1 2 3 is my second row, and maybe my third row is 2 0 2. Okay, so that's fine. So if I just execute this, it won't print anything. So it's good to print a, just to see how this will come out. So you see this comes out like this. So you see here, there is, when it prints it out cleanly. It says there is a square bracket outside indicating that what's inside is like an array, and then the first row is 1 0 1, second row is 1 2 3, third row is 2 0 2. Okay, so now you can go on and define any array, but it seems like you have to type it a lot and type a lot, right? So if supposing you want to input a 10 by 10 array, then you have to type all the elements, and there are a lot of shortcuts to define these arrays. You can define the ijth element in some way and then call it. You can do a lot of things. But you can also define a lot of standard arrays. So here is a bunch of standard arrays. I'll show you. There is something called np.zeros. Zeros, and then you can put zeros of, let's say, 5 comma 5. So notice what happens here when I do zeros of 5 comma 5, right? So it says it's an array, and then you can see it puts 0 dot because it wants to think of every number as a real number. Okay, so that's why it puts 0 dot. You can also do a d type equals here if you want to make it integer, etc. You can do a lot of things here. But this is an array of all zeros. So 5 comma 5. You can also make it 3 comma 5. So then you will get a 3 comma 5 array of all zeros. So this is a quick way to create large sizes of fixed things. In fact, Python is very powerful. It can do a lot of things here. You can write formulae for doing the ijth element and all those kind of things. I'm not talking too much about all that. So let's keep it small just for that. You can search and figure out these things. So instead of zeros, you can also have ones. Okay, so this is 3 by 5 all ones. You can imagine what it is. Supposing instead of ones, I want to have all twos. Okay, you don't have to worry too much. There's no twos command, but you can multiply this with 2. Okay, so notice what happens here. Okay, so that's good enough, right? So if you want a constant array of any size, you know how to do it, right? So supposing you want a constant vector, which is 5 3 comma 1 with 2 in it. You can just do this. Okay, so I hope this was clear. So it's easy enough to just put these things together, and you can also arrange vectors together. You can do something called v stack, head stack. You can arrange 2 arrays together, and it can do a lot of interesting things like that. So this is ones. A very common thing is the identity matrix. So that is usually called IE, np.IE. So by identity matrix is a square matrix, so you have only one parameter, so you can maybe do 5 here. So you see here, so that gives you the identity matrix. So from here you can identity matrix, you can create diagonal matrices, right? So of different types, so it's possible. Okay, so I hope you see there are lots of commands in Python NumPy available for creating matrices. So you can go look up how to create matrices in NumPy, what type of matrices you want, and be a lot of help. If you can just help for creating matrices NumPy, if you search for that, you'll see hundreds of pages giving you various options, and you can even also specify what type of matrix you want. A lot of help is there. Okay, all right, so we can create matrices now, and we've created a few of them. Okay, what else can you do with matrices? So what else is telling me is possible here? So let's just see. So this ampersand operator is a multiplication operator. Okay, so let's just do so if you want to do matrix multiplication, you know that if you have a 3 by 3 matrix, you can multiply on the right with x dot t, right? And you can multiply on the left with x, isn't it? So let's try that. So for that, the ampersand operator is useful in this. So you can do x ampersand a. Let's see what that is to that. So there you go. There you go, it did that, right? So x is 1, 2, 3, you multiply on the left with the matrix 1, 0, 1, you're going to get 9, 4, 13. Look at how easy it is. You don't have to keep track of anything else. You can also multiply A on the right, but you'll have to do X transpose, isn't it? So otherwise, the column row thing. So you can see here it's 4, 14, 8. Now, if by mistake you didn't do the transpose, you just did X, you'll see that there'll be an error. Okay. So because I was consistently putting everything into matrices, it will give you an error. If instead of this, if you did only like one-dimensional vector, so it will give you some valid answer here, which is actually not a proper matrix multiplication. So watch out for these kind of small things. Small syntax issues here there. You can make mistakes in computer programs, because computer program is not that smart. No, it will only interpret your syntax exactly. Okay. So here is something I want to show you. So you can do this kind of a product, right? So you can do x dot t and x, and this will give you so x dot t is a column vector, and then a row vector. You can always multiply a column vector and row vector, you'll get a 3 by 3 matrix, isn't it? So you get that. So you can do basic matrix multiplication with this ampersand operator. There's also other ways to do matrix multiplication. There's a function called matmul that you can use. You can do that also. There are multiple ways to do the same thing, right? So you can pick up a lot of these things with help. Okay. So you have to go online, search for it. You'll see a lot of things coming out. Try different things with Colab and make sure that you agree with what it's putting out. Okay. All right. So that is about matrices. How to start off with matrices in a simple way. Okay. So there are of course many other things that one can do, but let me not go into great detail. So you can see the commands that are there. They are sort of classified in NumPy into various sections. The first sections are matrix and vector products. You see a lot of products are there, inner products. You see matmul is there. So many complicated stuff is there. So these are things we have not learned properly. We can do that later. Okay. So I'll come back to decompositions later. I come back to eigenvalues later. Let's first look at solving equations. Okay. So one of the basic methods that we saw is to solve linear equations, and the basic method that's provided in Python is something called linalg.solve. So what is this linalg.solve? So let's see how to use that. Okay, what did I do? Okay. So here is how I'm going to use it. Okay. So I need a matrix A, and this matrix A for solve needs to be invertible. Okay. So solve, it's a bit finicky about that. So what I'll do is, let me redefine this matrix A. So I'm going to define A as np.array. Notice how we have to do this. I'll pick a simple 2 by 2 matrix so that I know, oops, I made a mistake, see. So 2, 1, and then you have this. This is my A. I'm going to define an X, which is again an np.array. We'll define it as a, no, I'm sorry, B, right? Ax equals B is what we are going to do. I'm going to define a B, which is a, I'm going to say 1. I want a column vector, right? So I want a column vector 1, 0. Okay. So I'm being consistent and careful here. This is okay. If you don't do this, Python will interpret it carefully. A lot of people will just say 1, 0. It works, but let's just be careful in what we are doing. Okay. So now how do I invoke the solution? I'm going to invoke it like this: np linalg. Notice how I'm keeping on typing it np dot. If you don't type np dot, it'll throw an error at you. Okay. This np dot is important because only then it knows I have to call NumPy. And then within NumPy, I have to call linear algebra package, and then dot solve, right? So this is how Python works. And then you can just do a comma b, and that will give you an answer. So you can store the answer, or you can just print it out and then see what it does. So there you go, it's put out the answer. So notice it's numeric, so it will be approximate. It won't tell you exactly what the answer is, but you might know that minus 1 by 3, 2 by 3 will give you 1, 0 here. So minus 1 by 3, 2 by 3 will give you 1, 0. So from here you can sort of approximately infer that the answer is minus 1 by 3, 2 by 3. So notice how linear algebra solution works. Of course, in this particular case, you could have done it by hand, but I want to show you that it's possible to do this like this. Okay. So this is, and of course, in larger examples, if you have a 10 by 10 matrix and you're solving an equation, then this is much easier, right? This is very hard. So maybe we'll see an example of that a little bit later on. Okay, so let me modify this a little bit. So let's say I make it 2, 4 here. So notice 1, 2, 2, 4. This is actually linearly dependent, right? So the rank of this matrix is only 1. It's not full rank. So it is a singular matrix. Okay. So now, but I know, for instance, that 1, 2 is possible, right? So if I say 1, 2, the 1, 2 column lies in 1, 2, 2, 4, right? It's possible. So, but notice what happens when I do linear algebra solve. Oh, it doesn't like it. Okay. So it says big error it's throwing. It's saying a lot of complicated things here, but finally it says singular matrix. Okay. So this NumPy's linear algebra solve cannot deal with singular matrices. If there is a singular matrix, it will start saying, even if there is a solution, of course there may be a solution, may not be a solution. Even if there is a solution, it will start protesting. It doesn't like singular matrices. Okay. So if you remember our theory, the thing with singular matrices is there is not just one solution, there are many solutions. So this linear algebra solve works only when there is a unique solution. In any case, if there is the matrix is singular, it is non-square, etc., it doesn't work. Okay. So how do we do this then? I mean, when it is non-square and all that, the only thing that NumPy provides is a least square solution. Okay, so you can't do solve, so you'll have to do least squares. Okay, so how do we do least squares? You can go back here and check. There is a thing called least squares, LSTSQ. You can click on this. You can go find its help. The help will tell you what it does, what it outputs, etc., right? So there's a very nice example here. So let me just show you also how least squares is going to work. So supposing I do least squares here, LSTSQ, it will give you least square solution. So we know least square solution always exists. There's no problem with that. So you will get a solution. So notice how the solution, there's lots of interesting. So there is some warning. I mean, you can sort of ignore this warning. It is giving you some advice on what to do. But anyway, that doesn't affect us. Okay. So here is the answer. The answer is 0.2, 0.4. Okay. That's what it says is the answer. I mean, most of us would have just said 1, 0 as the answer, right? But it's saying 0.2, 0.4 as the answer. It's the least square solution, isn't it? So 1, 0 is maybe not the least square solution. We know the least square solution is a specific projection, right? It's a little bit more complicated. So this least square solution is 0.2, 0.4. Okay, you may also find the least square solution. You know how to find the least square solution, right? So you do A transpose, multiply both sides by A transpose and then solve it. You'll get that. That might give you 0.2, 0.4. Okay, but there's also other things here, right? There's lots of other stuff here, and these are things for now. You can see if you look at the help, you'll see that this 1 is actually the rank. It tells you that the rank of this matrix is 1, and then these are some indicators of how dependable the solution is. It turns out when you go to larger and larger sizes, a solution may not be dependable. It depends on, may not even be that larger size. Even for 10 by 10, you can get some sort of noisy solution. So sometimes this is important. Okay, so this is least squares for you. I want to show you something here which is very nicely done. I think an example of a least squares fit. Okay, so there is an attempt to fit this example here that is there in NumPy help is here is data 0, 1, 2, 3. The y is given as noisy version, so y equals mx plus c. And he's trying to fit a straight line here, trying to find m and c. And there is a little bit of description on how that is done using least squares. You can see there's a matrix A that is being set up with an algorithm with a method called vstack here. You can see np.ones is being used. It's just a clever way to set up this matrix. Okay, instead of typing it out fully, you can also type it out. In this particular case, it's not that big. And then you can fit in a straight line and it gives you coefficients m and c. And then there is a way to plot. In Python notebooks, you can also plot. Notice there is another thing being imported here, matplotlib.pyplot. I'm not going to go into details. You can see it, and you can see you fit a straight line into something like this. So this is good help, right? So you can look at this kind of help wherever you find it, and it will tell you how to use all these things very well. Okay, good. So we have done this. The next thing we can do, if you go back to linear algebra help, is there's lots of other things that are here, right? So first thing is eigenvalues. So let's look at eigenvalues, right? So if you have a fairly large matrix and you want to find its eigenvalues, maybe it's It's a little bit confusing on how to do it, but since we have a very small matrix here, so we can try our eigenvalues with that. So, I mean, if I give you a large matrix, I'll show you a large matrix also. It will give you a bunch of eigenvalues, eigenvectors, which is good to see, but then you may not be able to quickly check it. But for our matrix here, we know what has to happen. So we can easily check this. So linear algebra dot EIG. So this is a function for eigenvalues. I'm going to simply pass this matrix A to it and see what it puts out. Okay, so it's going to put out some things, and you can see the eigenvalues. It gives you a nice format here. It says the eigenvalues are 0 and 5. So it's not surprising, right? So why should one of the eigenvalues be 0? It's not full rank, right? The rank is only 1. So one of the eigenvalues has to be 0. The null space is non-trivial, right? So null space vectors are there, and 0, 5, and then eigenvectors are here. Okay. So now this is a sort of shortcut to find out. If you know that the null space is there and you want to find null space vectors, you can just go pick up the 0 eigenvalue and then know that that vector corresponding to it is a null space vector. So you could have found the null space vector very, very easily here, but notice how it is giving it. It probably gives a normalized version. So you get something like this, and then this is also a symmetric matrix 1, 2, 2, 4. So you will have orthonormal eigenvectors. So it gives you orthonormal eigenvectors here. You can check that. So this vector is one of the eigenvectors. This is the other eigenvector. Notice it gives you an array as an eigenvector. Every column of this array, I believe, is an eigenvector. I think that's the output. So you should check all these things. What is the output? I should say results. It returns eigenvalues such that the column is the eigenvector corresponding to the eigenvalue. Okay. So you see here every column is an eigenvector. So here it was printed a bit oddly. So maybe what you should do. This is a good way to, you can do it as L comma V. Okay. So then what will happen is then you can print these things. So you can print L. It returns the eigenvalues. So eigenvalues in L, and then returns the eigenvectors in V. So if you see this, you will see 0.5, and then the array is printed properly. So the first column is eigenvector corresponding to 0. The second column is eigenvector corresponding to 5. Okay. So now you can make the matrix A a little bit more complicated. Let's say we make the matrix A as np dot array. Let's make it like a 4 by 4 matrix, right? 1, 2, 3, 4. This help can be a little bit distracting sometimes. 1, 0, 1, 1. I hope it is some reasonable matrix. Minus 1, 2, 1, 2. And then the last one, 1, 0, 0, 1. What do you think of this matrix? This matrix is reasonable. I don't know. I hope. Let's just run it. Okay. So notice what happens here. So you start getting a lot of things. So first is the eigenvalues. So you notice you're starting to get complex eigenvalues. Of course, there can be complex values, but look very, very closely. The first one is, notice this notation here, this E00. I hope you know what that is. E00 is basically floating point notation. It says into 10 power 00. So it's like nothing actually. 10 power 00 is 1. So it's 3.8 plus 0j, it says. Okay. Okay. So that's one of the eigenvalues. Okay. And that's interesting to me, because I think so it ends up being real. And then notice this last eigenvalue here. It's like, it seems to be complex, and it seems to be minus 4.10 power minus 16. Okay, so my guess is this is actually 0. Okay, so this matrix is likely to have rank 3, and somehow I don't think I cooked it up like that. Maybe it is rank 3. So because of that, you actually have a 0 eigenvalue, but instead of putting out a 0 numerically, the best thing is able to find is this guy. So let's check the rank. I think NP has a rank method. I think maybe does it have a rank? No, it doesn't lack rank. See, so supposing I want to find a rank of a matrix, so what do I do? So you can search for. This is what I do as well. Okay, so linear algebra dot matrix underscore rank. So that's what we're supposed to do. So let's try that and see if it works. So NP doesn't have rank. So linalg dot rank, is this there? No, maybe not. No, it doesn't have it, but looks like there is something called matrix rank. That's what I'm told. There you go, 3. Okay. So this is how everybody does it. I mean, you can't remember everything. So you just go search for it and then look at the search result. Matrix rank was there and then 3. So notice, not surprisingly, the matrix rank is 3. So this matrix has rank 3. If you did elimination, you could have found out very easily that this has rank 3. So this eigenvalue, while it is some complicated looking complex number, it's actually 0. Okay. So notice this again tells you something about what are the pitfalls of doing linear algebra on a computer. So because of numerical inaccuracies, instead of getting 0 here, you are getting this big number. Okay. There are other computer systems which may do this better, but still you have to be careful. When you see this number, you should something should click on and say, okay, maybe there is an accuracy issue. This is actually 0. That's how it's working. Okay. So it's got 2 real eigenvalues, 0 and this 3.80 something. And then there is a pair of complex conjugate eigenvalues. See, this also has to happen. No, this is a real matrix. So if it has complex eigenvalues, it will be complex conjugate. Okay. So now comes how to interpret the eigenvector. So it's, look at the print. It's a little bit confusing. No, so it's a 4 by 4 matrix. Every column is a eigenvector corresponding to it, but the first column is difficult to read here. No, so this is this one, this is this guy, this is this guy, and this guy. So these 4 together are the first column. So the eigenvectors are all real here. Okay. So likewise, the last one also, the eigenvectors will be real. So notice this guy, this is actually a null space vector, right? This is corresponding to 0 eigenvalue. So it's a null space vector. So notice that you get that. So maybe the null space vector can be quite easily inferred as well. Okay. The other 2 eigenvectors are likely to be complex. So notice that this guy is complex, the second eigenvector corresponding to the complex number. So because it's complex eigenvalue, has to be a complex eigenvector, otherwise it won't work out. Okay. So this is a slightly larger example. So there's lots of other things you can do with eigenvalues. So once you find eigenvalues, it's very useful. Okay, so that's eigenvalues for you. Let me close with a quick look at something called QR factorization. I'll tell you why this QR factorization is interesting. So this QR factorization of a matrix is very interesting to look at. So let me just quickly go through and tell you what this QR factorization is. Okay. So if you have a matrix A, it can be an M cross N matrix. You can take the columns of the matrix. So let's say the first column is here. Let me call it A1. Let me call the second column A2. There are N columns. Okay. So you can take these N columns and run Gram-Smith on A1 to AN. What will you get? You will get V1. So it depends on the linear dependence or independence, right? So let's say so some k, the rank is k. Let's say the number of linearly independent guys here. So the dimension of the subspace spanned by A1 to AN, maybe it is rank k, right? So then the Gram-Smith will go up to Vk, right? After that, it will just become 0, isn't it? So I hope it's clear to you. So so some of these columns may be linearly dependent. So maybe you can start with the linearly independent case if you like. So let's say A1 to AK are linearly independent, and after that they are linearly dependent. So I'm just assuming a simple case here just to show you how this is going to work. So you will get V1 to Vk. So the point is, you can A1 and V1 are like linearly related, right? So so how does it work? So span of A1 to AI is the same as span of V1 to Vi, isn't it? Right? So everything you could get with A1 to AI, you can get with V1 to Vi, and this is actually orthonormal, isn't it? This is your Gram-Smith Gram-Smith process run on the columns of the matrix A. So equivalently, the Gram-Smith process can be written as Q times R, where Q is an orthonormal matrix M cross M. So you can, if the k is less than m, you can always extend it to get an orthonormal basis, right? So orthonormal matrix. Then R is an upper triangular matrix. Okay. So this is the story here. So this is very important and interesting to look at. So this is called the QR decomposition. It comes from the Gram-Smith process. So you can see why this R will be upper triangular, right? So once you have the Q will have, basically Q will be V1, V2, so on till Vk. After that, this Vk plus 1 to Vm, this is a extension, okay, orthonormal extension. Is that okay? You do the V1 to Vk using Gram-Schmidt, and then you extend it to get the basis for the full vector space M cross M. So this becomes M cross M. And now what is A1? A1 is just some scalar into V1, isn't it? That's how the Gram-Schmidt works. A2 can be written as a linear combination of A1, A2. I mean, sorry, V1, V2. V1, V2 alone. Okay. So A3 likewise. So likewise till AI, you can write it as linear combination of V1 to Vi, right? This will go on up to AK, V1 to Vk. After that, it will all remain the same. So in fact, AK plus 1 to AN, it will all be linear combination of V1 to Vk. Okay. So once you write like this, what happens here? So the first column, so if you want to write A1 to AK and then AN all the way, the first column, so you write Q as V1 Vk, and then you got the additional guys, right? So it doesn't matter what they are, and then you can have a, so this will be an M cross M matrix, and then you will have a M cross N matrix, and this will just be, the first one will just be C followed by a whole bunch of zeros. So if you do this, this column multiplies the columns of Q, right? So this is A and this is R. This column multiplies. So A1 is just linearly dependent on V1, right? C into V1 in the Gram-Schmidt, that's how it works. So it's just C into V1. And A2 is a linear combination of V1, V2. So you will only have some non-zero value here, non-zero value here. After that, everything will become 0, right? Just V1, V2 is enough to give you A2. Likewise, V1, V2, V3 is enough to give you A3. So you will have automatically an upper triangular form here. Okay. So likewise, I mean, eventually at K it will stop, and after that it will just become all only the top part will appear, nothing below will appear. But anyway, so it's at any rate, this R is an upper triangular matrix. Okay, so hopefully you can see why the Gram-Schmidt is working out as something called a QR decomposition. So this kind of writing Gram-Schmidt as a matrix product is called QR decomposition, and most of the linear algebra computer methods will give QR decomposition. Okay. So now what's the point of this? So supposing I have a matrix A like this, I want to find the column space, right? So I know the column space has got dimension 3. How do I find the column space? How do I find a basis for the column space? In fact, how do I find an orthonormal basis for the column space? You can do that with a QR decomposition. So you just take NP dot linalg dot QR of A, do enter. So it's going to give you the QR result. It tells you the Q array, it tells you the R array, and you can see that the R array is ends up being upper triangular, or in this case. So it may not be exactly upper triangular in the complex case. It usually, I mean, if you allow for complex values, it will be upper triangular. Maybe there is a way to specify that here. I think, let me just see. Okay. Usually there is a way to say whether you want to do complex or real. If possible, you should do complex, because I think, but I think that's okay. It's just Gram-Schmidt, so it should be okay. Yeah, so QR decomposition should be okay. So you're doing Gram-Schmidt, so you should get a reasonable answer, real or complex. I'm just trying to see if we can print it properly. So let's just do this. Let's return Q and R. Yeah, Gram-Schmidt should be okay. The Schur decomposition is the one that needs complex. So I'll come back to that also. So you can do print Q, print R, and then just run it. Now you can see the QR decomposition at work here, and you can see how. So notice after a certain point the R becomes 0. Okay, so this clearly indicates the rank is 3. Okay, and the first 3 columns here are going to be your orthonormal basis for the whole vector, whole column space of A. Okay, then you can see that it's just only the first 3 matter. After that, it's become all 0, right? The fourth one, I mean, of course, the column is not 0, but only the first 3 columns are involved in the thing. The last 4th column was just a extension to get you the basis of 4 by 4. So this is a way a QR decomposition works. So hopefully just go through these decomposition, make sure you tie it up with the theory, you understand how it goes. Let me just repeat this once again. So this A had only rank 3 matrix. So out of the 4 columns of A, only 3 are sort of linearly independent. They're enough. The 4th column is going to become linear combination of the first 3 in some sense. And that's borne out here very clearly when you do the QR decomposition. It says the first column is a multiple of this guy, second column is just a multiple of this guy, third column is a combination of the first 3 columns here, and the 4th column is also a combination of the first 2. Okay, so the 4th column is not linearly independent here, it ends up being linearly dependent. See, the 3 rank 3 are coming. So the basis for the column space will just be the first 3 columns here, and it will be an orthonormal basis for you. Okay, so the QR decomposition is very, very useful for that matter. In fact, there's another decomposition called SVD, singular value decomposition, which is used extensively today in various places, and that's one of the first things that you would do. Okay, so as far as describing about these packages, one can go on and on. I mean, there's no reason to stop it. There's so many other interesting things that you can do with these packages. Is this unending thing that you can do here, but for our purposes, I'm going to sort of stop at this point, okay, and not show you anything more which is very extensive. I'll just show you the MATLAB window alone. A MATLAB window looks like this. Scilab and Octave also will sort of look like this. You can start typing commands here, and it has a lot of these things. So it's got a eigenvalue command. You can ask for help here, and hopefully it should come. Let's see, yeah, there you go. So you see eigenvalue command is there. It gives you a lot of extensive help, and if you go online and search for linear algebra using MATLAB, you'll have extensive courses which talk about how to use MATLAB for linear algebra, many of them free. You'll be available and you can learn how to do it. The syntax will be slightly different from what I showed you in Python, but it's doable. Okay, so hopefully this was a good introduction for you for how to do linear algebra on a computer. Please explore this on your own. Become very comfortable with some computer algebra package on which you can do all these vectors and equations and all that. It will help you tremendously in the courses that are going to come later on. Okay, thank you very much.